In recent years, research about materials has entered an era marked by an unprecedented surge in data stemming from both experiments and computations. We see the needs, and in fact we also see already successes of a radical change in how information is retrieved, handled, and how research is performed. This integration of artificial intelligence and its subset machine learning has become pivotal in addressing all these challenges at all different levels. As noted here, we are part of a transformative shift of how materials research is being performed. This is called the fourth research paradigm of materials science. Let me note that the term new paradigm does not refer to a new method. It refers to a new way of thinking. A key issue here concerns the identification of correlations, which is quite different to the classical scientific approach of materials science, which is aiming at causation. I will discuss later in more detail with specific examples what I mean. In fact, I will describe certain AI methods that bring some causation back. And we feel that this is important indeed. So this brings me to the concept of materials genes. These are basic materials features or basic materials characteristics that play a similar role as genes in biology. Such features could be local structures or certain aspects, local structures of the solid, or certain aspects of the wave function of the atoms that build the material. These materials genes correlate with a property of interest, and the property of interest may be a certain catalytic performance, or it may be a certain value of the band gap of a semiconductor, just to name two examples. However, the scientific relationship between the materials genes and the property is not known, and typically cannot be expressed in terms of a meaningful equation. Therefore, the relationship between these materials genes and the property of interest is not described in terms of scientific laws. It is not derived from scientific laws, but the correlation is described by what we call rules. This also means that we don't deal with clear predictions. Instead, correlations are described by statistics. Thus, we predict probabilities or probability distributions. This means we predict a mean value and, hopefully, also an uncertainty, that is, a variance. Again, this is why we use the concept of genes. A combination of a number of certain genes predicts, in biology or medicine, for example, a 70% risk for getting a certain type of cancer. And the analog is true for materials genes. A certain combination of certain basic materials parameters tells with a certain probability about the material's properties or function of a material which is not known so far. For example, it predicts that there is an 80% chance that a certain material, which is not known, has a band gap of 2 electron volts, just to name a specific example. This is what I mean with a new way of thinking, where we now largely ignore theoretical physics, largely ignore physics laws and physics education, but we are looking for correlations instead. In a more positive phrasing, I like to say that we acknowledge that there is a higher complexity in the world than which can be described by classical mathematics and by using partial differential equations to write down scientific laws. In the real world, there is not just one process, but there is a high intricacy of many processes. I wanted to discuss the importance of data-centric material science and the daunting challenge for the discovery of novel materials. Recently, we have seen impressive neural network studies in the literature that predict unbelievable big numbers of stable materials, billions. However, we feel that the creation of materials maps is important, as only this provides an educated suggestion where in material space we should concentrate the search for better functional materials. I use only one example in my talk, namely the search for thermal insulators, but we have actually done many more. For example, in heterogeneous catalysis. For thermal insulators, we were able to identify materials in a region of material space which was hardly explored so far. Thus, we have a workflow which steers the search efficiently towards finding materials with the desired target value. Typically, the data situation in material science is not extensive. Thus, many AI methods are not applicable. Random forests, Gaussian process, kernel-ridge regression often work and have been briefly compared in my talk. CISO provides comparable, maybe just slightly better performance, provided that the relevant primary features and the relevant operators that connect these features are offered. CISO provides a good description, and this description is interpretable. If the CISO description is not good, this tells that we missed the relevant primary features or operator. Despite some success, it is also clear that material science needs further advancements of artificial intelligence and machine learning methods. And in particular, we need a more reliable uncertainty quantification than what we have to do. It is important to know how reliable is an AI description and what is what we call the domain of applicability of the employed AI model. In this context, I also mentioned active learning, and here is very important. It is very important to combine the machine learning approach with an appropriate acquisition function concept. Also here we urgently need better uncertainty quantification. Some analysis of how machine learning and acquisition functions may be combined was recently discussed in this paper here. Let me finally acknowledge the financial support of this work by the European Research Council and my advanced grant on thermal and electrical conductivity from first principles. And I'd like to acknowledge some people who were significant in the work and understanding that I had discussed, namely Tom Purcell, Lukas Fopper, Mario Bolai, and all the other co-workers in my group in Berlin. I thank you for your attention. In case that something was unclear in my talk, or if you have comments, please let me know. Thank you.